Good afternoon, everyone, and welcome to Going Reactive with Typesafe. My name's Adele, and I head up our community partner team here at eSynergy Solutions. We are really pleased to be hosting today's webinar, and I just wanted to give you a short introduction to eSynergy. So, eSynergy specialise in open source and cloud resourcing. We have a dedicated team focused on placing contractors and permanent teams around development and architecture. So if you are looking for a new opportunity or looking to build out your team, please do get in touch. I've popped my colleague Neil's details on the screen. He heads up our development and architecture team, so please do get in contact with him directly. So now just for a bit of housekeeping, if you have any questions throughout, please use the chat box, which will be on the right-hand side of your screen, and all of your questions Lutz will answer at the end of his talk. We'll also be sending out the slides and the recording by tomorrow by email, so you can expect that from us tomorrow. So now I'm going to hand over to Lutz, who's the solutions architect at Typesafe, that's going to be presenting for us today. So introducing Lutz.
Talk a bit about the Typesafe Reactive Platform and also our operations tool, Typesafe ConductR. So why are we talking about this in the first place? Well, to motivate this, I'm going to give a little bit of a historical, if you will, background. If you look back 10 years ago, that was the before iPhone age, I like to call it. That was before everybody had smartphones. We would use the internet maybe with a desktop computer, with a laptop, and the way we built internet sites was usually rather monolithic. They'd have one or two big servers, maybe with some failover and a big database server in the background, but it was really not that fancy. Of course, things have moved on since then. Today, we have loads of devices that are connected to the internet. Your TV set is probably connected to the internet, your gaming console, your mobile phone, your tablet computer, and of course we still have desktops and notebooks. And we use these mobile devices all the time and are online all the time. And also if you look at how systems are built today, of course that has changed as well. Now we use a lot of virtual nodes. We rarely have a system that only consists of a single or two servers. It usually spreads among quite a number of nodes. And also we split up our systems more to services. And this is only gonna progress, right? In the near future, we're gonna have even more devices. With the Internet of Things, billions of devices are gonna be connected all the time. Your light bulbs, your car, your watch, maybe your lawnmower, what have you. Plus the other trend on the server side will move on as well. We're gonna see much more applications composed of small services and spread out over a huge number of nodes. So these are the changes we see in the overall landscape of system architecture. But also if we look at hardware over the last 10, 15 years, there are a lot of changes to be observed there. So we used to run on single machines, now we run on clusters or in the cloud. And we used to have single core processors, but now every machine you get has a multi-core processor. So parallel is really has become the default. You want to build your systems, you want to build your programs so that they leverage the multi-core architecture of your system so that threads can run in parallel. RAM used to be scarce and expensive. Now we have pretty cheap RAM, and we can actually keep a lot of data in memory. We can run things like in-memory databases now. But also disk space has become cheap. So the urge to delete data has become less pressing. We can basically keep data indefinitely. We can just store data in our database and we don't have to delete it at all. Networks have become much faster. Now with a fast network, a network access can be faster than a disk access. So new replication scenarios have come up. It's easier to have a distributed state in your application across the network and have nodes that can communicate in a very fast manner. And if you build an application now, there's some probability that's going to be in the internet and that you're going to get a lot of users. So you end up with a lot of concurrent users. You have to deal with that as well. The data we deal with has become much more. We talk about big data these days. You have huge data sets that need to be transferred and that need to be analyzed. And lastly, people are still very impatient, or even more so. Now the requirements we have towards the applications we use have become more demanding. We now expect systems to be always on. We use them almost as if it was infrastructure, something like the phone network or the power grid, where we just rely on it and just assume that it's always there. That's the way we use services like map services or your email service, your social networks. People are always online and expect these to be always there. And some business models rely on that as well. If you use, if you use the phone to get a ride somewhere or to find a car that you can rent that is just parked somewhere, these services, they just need to be there continuously. So why am I telling you all this? Well, if you look at how these modern applications are built, it's really not built anymore the way we used to. Some of the standards that a lot of people still work with, like a prominent example being the Java Enterprise Standard, these specifications have been developed around the turn of the century, and they've been built for systems as they were made in 2005 maybe. But if you look at modern systems now, they've actually found a different way of architecture. You see them much more highly distributed and in a more fail-safe and resilient way. But there was no consistent terminology for that, and that we found that nobody ever sort of captured the essence of what brings these modern systems, what these modern systems share. So what one of our founders came up with, Jonas Bonnier, is the Reactive Manifesto that you see here on the screen. And of course, I don't expect you to read it here on the screen or the small print, but you do see the URL on the page, and I would highly recommend that you go to that website occasionally and read the Reactive Manifesto, and you're going to find that quite interesting. Actually, right here, you see this little picture in the right-hand corner there. We're going to take a closer look at this. So the principles that we found behind modern, always-on resilient systems are the four reactive traits you see on this slide. These systems have to be responsive. To be responsive, they have to be elastic and resilient, and we achieve this by being message-driven. So we're going to look at these four traits in a bit more detail. When we say responsive, that means that they are always available to the user and that they always provide an appropriate response, that they give the chance to have an ongoing dialogue. And this seems self-evident, but the important thing to understand is when we say responsive, it means responsive all the time, not only when everything's going fine and under blue skies, as people say, but being responsive also when the load is heavy, when everybody wants to go to your website, when it's prime time, when you are Netflix and people come home after work and want to watch a film, then that's the time where you have to be responsive, right? Well, you have to be responsive all the time, but you cannot stop being responsive at that time. And well, when we talk about distributed systems, failure is inevitable. There will always be parts of your system that will fail. You cannot rely on, if you have 10,000 nodes and these nodes have an uptime of 99.99%, well, if the number is high enough, then there's always going to be one node at a time that's not functioning. So the bigger the numbers get, the more likely it gets that something fails. The more distributed you get, the more likely it becomes that something fails. So your system has to keep working though. You have to stay responsive in the face of failure. To be responsive, one of the most important things is, of course, to scale. You have to be able to add hardware to your setup and then be able to handle more concurrent users. We chose the term elastic though over scalable, because we think it's just a better way of expressing that, because we also want to be efficient on a smaller level, on the one node level, if you will. As we said earlier, modern systems have parallel hardware. You have multiple cores on your computer. You might have multiple sockets on your main board. So in a modern server system, it's easy to end up with 30, 40, 50, I think up to, or you can probably get up to 250 cores, but you get up to I don't know, more than 50 cores per socket. So you really want to leverage that, and you really want to build your systems in a way that this hardware is used efficiently. But the other trait you still want to have, you still want to be able to add more hardware to scale up. And also you want to be elastic over time. You want to be able to scale up, but in times where the demand is not that high, you want to be able to scale down as well and save cost, because even in the cloud, you still have to pay for your instances. And you want to leverage the possibility to fire them up quickly and to shut them down quickly. If you just have a huge number of nodes running all the time, then you don't save anything. So you really want to be cost efficient in terms of utilizing the existing hardware, utilizing the existing multi-core architectures, and also being able to scale up and down automatically. Another very important part is resilience, of course. And when we talk about resilience, and the reason why we put it up in these 4 traits is we think that this is something that has to be a first-class concern in your application, not an afterthought. It's not about building an application and then think about error handling a bit. And it's more, what we say is embrace failure, let it crash, expect that nodes fail, expect that interactions fail, expect that the network fails. Because, well, after all, it's going to happen. And even if it doesn't, it's better to sort of expect the worst and then you can be happy if it doesn't happen, but you have been prepared. And, well, if your system runs long enough or becomes big enough, failure will happen. So it should be a first-class construct in your language. You have to anticipate it and have to deal with it actively. How can you deal with it? Well, if you say failure is going to happen anyway, the one thing you have to do is you have to isolate it. You must make sure that a failure in a subsystem or in an external system you use or in a network component you use does not contaminate the whole system or bring down the whole system or make the whole system slow. You really have to isolate it and manage it. And ideally, your system is going to be able to recover from this failure. You can, in terms of hardware, say a node really breaks and the hardware breaks and you have to exchange the node, and it should be seamless to the user. The node will go down, you can replace it with another hardware, and you can spawn up another cluster node on that machine, and the application will be just like before. So to achieve this, the message-driven part, I almost forgot about that. We found that a proven approach to achieve this is to go asynchronous completely, and to use a message-driven approach. By using a message-driven approach, and we're going to look at that a bit more on a slightly more technical level on the following slides, so bear with me if it's not completely clear right now, but what you have is a decoupling of the sender and the receiver, and that makes it really easy to go asynchronous. It really requires you to go asynchronous, and once you're there, it's also really easy to go distributed. So the things we wanted to achieve that we mentioned earlier, to leverage your existing hardware with parallel constructs, and also to be able to scale up and out, this is enabled perfectly with message-driven approaches. And well, we Typesafe have a certain message-driven approach based on actors, and we have a whole set of tools that allow you to build reactive applications, and you see them on this slide. So it's Scala, the programming language, Akka, the actor framework, and Play, the web framework. We're going to look at these in a bit more detail, especially Akka. Akka, the actor toolkit. So the actor model is nothing new, really. It's been brought up in the 70s by Carl Hewitt. But it's really become popular in the telecommunications industry. And Ericsson, the Swiss telecom hardware maker, is very famous for their own programming language, Erlang. And they used Erlang and the actor system in Erlang to build the software that they run on their phone network switches. And that turned out to work incredibly well. So they were really able to build long-running systems that could scale very well. And I think most people would agree that phone networks work pretty well these days. And there's a lot of software in the background that we're not always aware of. So the idea of Akka is to take this actor framework and bring it to the JVM. We saw that this architecture is a proven approach to build resilient and scalable systems, but we also want to be able to leverage the Java virtual machine and the whole ecosystem around that, the huge amount of libraries that's available there and all the other proven technologies on the JVM. So what Akka allows you is to build highly concurrent, distributed, and fault-tolerant event-driven applications on the JVM. And we're going to look at the distributed, the fault-tolerant aspects a bit closer. The value that Akka gives you is that it gives you the actor model as a unified model. So in your programming, in the style that you write your code, you don't really have to distinguish between communication on your local machine, where you'd, in a more traditional approach, where we'd use multi-threading and have maybe use locks and synchronized blocks and some way of shared mutable state for the threads to communicate with each other. And then the remote approach, where we might use, I don't know, a REST service or RPC or messaging. So Akka really unifies this, and by this gives you a simpler model to achieve this, to achieve concurrency on your machine, and also to achieve distribution, because you can basically, by configuration, move actors to other machines and thus distribute your application over the network. And as an added bonus, if you will, it gives you a very good approach to fault tolerance, and that is the supervisor model, model of supervision. Also something we're going to look at a bit closer. Let's look at the concurrency aspect first. So the nice thing about the concurrency approach in Akka is that within the actor, you don't have to worry about concurrency at all. Actors get messages and process these messages, but within this process, it's like working on a single thread. Right? You have the guarantee that this message is going to be processed by one thread, and this processing is not going to be interrupted, and there's not going to be a switch. So because actors share nothing, because it's only immutable messages that are sent between the actors, and the actors can really only send messages themselves or spawn new actors. So, you can never access the inside of an actor, so you don't have to worry about locking, you don't have to worry about synchronized blocks, you don't have to worry about thread synchronization, communication, all this stuff. So what it really, even if at first it seems, oh, it's something, I have to learn something new, it's complicated, I have to think in terms of messages and actors, it's really meant to make the whole concurrent programming much simpler, much more, much safer really, less error prone. Because after all, if you've done the debugging multi-threaded programs, it's actually quite hard. This message passing model is since it's asynchronous anyway, it doesn't really matter where the actor you send the message to lies. So it's the default idea is really being distributed. The default is really send the message over the wire. We don't always do that though. If the actor you send the message to is in your local actor system, the message will not be serialized and will not use the TCP stack. So there's an optimization going on where it says this is a local messaging, I can just pass the reference to that other actor. But that is really, so that is the special case. It's not something, not an approach where you build your program locally in your system and then add on some remoting and then say, oh, I need to go distributed and now I have to plug something on here. No, the architecture has has a distribution in mind from the start, but of course optimizes if locality is given. So how does this work technically? Oh, well, not on a code level. We're not going to look at source code, but let's dig a little bit deeper. Not just talk about the concept and look at some details of it. So the action happens in the actor, and but you, as I said, you can never access the inside of an actor. The only thing you can do with the actor is send a message to it. What happens though is that when you don't get access to the actor itself, you get an actor reference, and then that's where you can send a message to. Well, what happens to the message? Well, what happens underneath is that every actor has a mailbox. So the sender will send a message, and the actor reference you have is not really a pointer to an actor. It just points to the mailbox of an actor. And you have a dispatcher that schedules threads, and these threads will take the messages out of the mailbox and pass it on to the actor. And as you can easily imagine here, if you look at this, you send the message through the actor ref, but where the mailbox lies or where the actor lies doesn't really matter in this case, right? You send a message through the actor ref, and the operation for you is done. Also, the call, because it's all asynchronous, right? The message sending will return immediately, and your thread of execution can move on. But now the message can be sent in the mailbox of a remote actor, so the mailbox also will be on another machine, and there the actor will dequeue the message and process it. So there's really no difference in the way you invoke an actor and the way you send a message. There's no difference if the actor is local on your machine, if it's maybe a set of actors. Actually, this actor reference can also represent a router that will load balance over a number of actors, or it can represent a remote actor, and still for the sender and the message, it's the same thing. You send the message in exactly the same way. Just by configuration, you can say, okay, this actor is actually created remotely. Actually, it can be a whole cluster. It can be a cluster router. So there can be a cluster of actor systems, and the router will distribute the message over other remote actors. So it's really easy to go from local to remote, or from local load balancing to load balancing in the cluster with actors. So this is the distribution part. Talking about resilience or fault tolerance. Well, we've just talked about how the message sending and the actual dequeuing and processing by the actor is decoupled. So you can imagine that this has some implications on the error handling as well. If an error happens in the actor, you don't really have a view on that. It's not like an error happens in your thread of execution, where you get the exception and the stack trace, because of the sender and the actor processing the message will run on different threads. There's a way to handle that, though, and as it happens, that's actually a very meaningful way, because it doesn't always make sense that the user of a service is also the one that deals with errors. Let's look at that in more detail. There's a very simple example that I think illustrates this very nicely, and that is a vending machine, in this case a coffee machine, where you can get coffee, but you need a key, or you need to have some card or whatever to refill the beans. It's freshly brewed coffee. So you're a programmer, you want to get a coffee at the coffee machine, you insert some coins, you get an error message, not enough money. So you put in more money, you get your coffee. That's all fine, that's all good. So this is the kind of error message you can deal with. But say you want to get some coffee, you put in some coins, and then you get the error message, there are no coffee beans. What can you do with this information? You're not even capable of filling up the coffee beans. You can't open the machine. So you shouldn't really be the person to handle this error. How should it work? You insert the coins, somebody else, the service guy, the guy from the coffee company, he should be notified. He should come and add more. Refill the bean supplies, and then you can get your coffee. So to come back to our software terminology, the client has a request to the service, and there might be some validation going on, and the service might give a validation error and say, this is the values you provide are not plausible, are not within the range of what I accept. And then it's correct that you get this validation error. But if something fails completely, if you just want to throw an exception, you say, I can't go on like this, then that shouldn't affect the client. Then somebody else should take care of that, and that will be the supervisor. And for the supervisor, you can define a strategy how the supervisor is to manage the failure. And this is a very, very useful approach, both in terms of the way you separate the concerns in your program. You sort of take out the error handling concerns out of the client and put it in the supervisor, and also because with these supervisors, it's really easy to create a hierarchy. So in Akka, you get this by default. If you create a new actor, the actor you create, the new actor from, will be the parent of the new actor. It will be the supervisor of the new actor. So with a topology like this, with a supervision strategy, what you can achieve is that you can easily isolate failure by picking the right supervision strategy. For example, if a node fails, if a node goes down, maybe here our supervision strategy is to just, well, we let it crash, we just create a new one. An actor had an exception and fails, so we just create a new instance and start anew. That's one possible strategy. And as I said, this is really easy to achieve with supervision in actor systems, and allows you to isolate failure nicely. And again, that's a proven concept, not only in software development, but in shipbuilding. You want to isolate failure, and you want to make sure that if you have if two ships crash, or if a ship hits the quay, you don't want the ship to sink, possibly. You want to compartmentalize failure and manage it locally, and by this avoid a cascade of failures. And what they call it is bulkheading. So what you can do with Akka, with a actor supervision strategy, is actually achieve this kind of bulkheading, the same as people use to make ships less sinkable. You can apply to your software to isolate failure and to manage it locally. Okay, that was it about Akka. We looked at the distribution aspect and how actors and sending messages to actors allows to go remote easily and to load balance easily, and how the supervision approach allows you to isolate failure and to use bulkheading to structure your program. Now, maybe you've built your great actor-based application that's very elastic and resilient, but of course you want to show something to the world. You need a nice web interface. And here we offer the Play framework, which is a very good match for reactive applications. Because itself, it's built completely asynchronous, and thus helps you to stay within the same model, rather than plugging something, a synchronous thread for request-based framework on top of your super elastic scalable actor system, and thus breaking the effect. You can stay within the same logging and have a completely asynchronous web framework. That's internally asynchronous. It doesn't mean you can only do WebSockets or whatever. You can still do regular HTTP requests, of course, request response, but you can actually handle, you can easily, with a rather simple machine, handle tens of thousands of concurrent requests, because the way the single requests are handled is completely asynchronous. This has some implications in terms of how it runs. It's actually container-free in the sense of it does not run on an application server. These are standalone applications. Play itself, if you write a Play application, you will not have an HTTP session or something like that. You don't really have the statefulness of traditional web frameworks. It's really opinionated about statelessness. And when you want the session logic, you either have to involve the client in that by using cookies, or you can build a stateful application with Akka where you store your state, but keep the web layer stateless and thus linearly scalable with Play. And Play is really a full stack framework. It even comes with a couple of nice plugins to allow you to use CoffeeScript or less or things like that. So the integrates a lot of front-end technologies. So you can build full-scale modern web applications, single-page applications that only communicate via REST and JSON. It comes with a nice, easy-to-use JSON library, which is also very fast as it happens. It fully supports WebSockets. So really anything you can think of in the web layer, I think, can be served by Play. And it plays really well with Akka and reactive applications. And lastly, the programming language. It's probably important to note that you don't have to use Scala to use Akka or Play, but we use Scala to build these frameworks. And while reactive programming is not tied to any programming language, we learned that functional programming is really very beneficial for reactive programming. Because what you want to achieve is being asynchronous and non-blocking. You want to be lock-free And this is really helped by having immutable data structures. The way you think in functional programming is not so much in terms of mutable objects that have an identity where you change the state of the object. You rather structure your program in terms of functions and values that are put into these functions. And ideally, the function will be pure and have no side effects. So whenever you put the same value in, you'll get the same result back, completely regardless of anything around that function or any state in your application. So, of course, there are limits to that. But it turns out that a big amount of applications we build, or a big amount of things we want to express in applications, can be expressed in a purely functional manner. So you might have, for interaction with the outside world, with the user, you might have a thin layer of imperative code, but in your core you can really be functional, and that helps building parallel and reactive applications. And so, and of course, for this, you need strong support for functional programming in your programming language, and Scala provides that. But just as a little reminder, Scala is not a purely functional language, or does not claim to be that. Scala really tries to be a unifier and to bring object-oriented programming and functional programming together. We think that a lot of ideas in object-oriented programming are good, and the object-oriented approach is actually good for structuring your code base. And on a higher level, it helps you to interoperate between teams, to define boundaries between modules. So there are a lot of ideas, a lot of good ideas in object orientation. But on the smaller scale, where it's about your algorithms and the details of your code and how you express your business logic, there we think that the functional approach is much better than the imperative one. And so it's actually, well, there's no reason not to combine these two. There's not really addressing the same level, so you can be on a higher composition level very object-oriented, and on a lower algorithmic level be very functional. And also, two other things that Scala unifies is a pretty lightweight syntax with type inference and with very little boilerplate code that you have. A lot of Scala programs are pretty dense and look like written in the scripting language. But we do have, just as in Java, we have a compiler, and the compiler will check the types and thus will give you feedback early if anything is incorrect. So you have a lot of things that the compiler will find out, and you don't have to learn during testing or even later during runtime, maybe even in production. So we found that especially when teams get bigger, when systems get bigger, there's a huge value in having static typing and strong typing, and that the compiler can really help you a lot there. So Scala, the claim of Scala, and I think it reaches up to this, is to unify both object-oriented and functional programming, and also to unify a lightweight, very productive approach where you end up with a small code base with a strong static typing. So now we looked at the development space. So now you've built your reactive application, but the same challenges that we addressed there you also have at runtime. You want to be able to run your services or to break up your application into services. You want to have the same level of isolation we talked about in Akka. You want to have that in the deployment world as well. And so it's quite likely that your application is going to run on a couple of nodes. Here, for illustration, we assume you have 3 nodes where you run your application of, and your application is composed of different components. So you want to be able to run these components in isolation so that the failure of one does not affect any others. You want to be able to be elastic as well. You want to be able to scale up and down these very easily. So how do we achieve this at runtime? Well, we built a Typesafe conductor for this. I'm going to go into a bit more detail in the following slides. Typesafe conductor is both for, well, I could say both for developers and operations people. Of course, nowadays we don't always have that. we often have a DevOps scenario where developers also continuously deploy, more or less continuously, or where you have short iterations and a lot of deployments. And of course, we want to support that. ConductR is well integrated with the development process. It actually comes as or part of it comes as an SBT plugin that allows you to create the unit you want to deploy. We call it a bundle. So you use SBT to build your little distribution, your bundle, and this can be this will be your code combined with some basic configuration, and this can be considered immutable again. So you can build this, and this can be going through different deployment stages without being changed. So you always know exactly what's running where, and the configuration is part of that. So there's not I get away from the confusion of what exactly is configured where or what's deployed where. There's a unique identifier for each bundle that includes the configuration. You can test this locally, and you can, of course, push this through your deployment pipeline, and you can clearly mark which external configuration is necessary, or you can clearly express that in your configuration. And this, of course, is something where the boundaries blur between development and operations, because that would typically be an ops task to say this is going to be the external configuration of the staging system, the pre-production system, integration and test system, production system, whatever systems you have there. So the actual production or staging infrastructure will be maintained by the ops people, and they will also take care then of the external configuration. So it's really spawning both of these roles. I'm going to pick out 4 basic capabilities of ConductR, and by this hopefully it becomes clear what ConductR does and what why it is useful. So ConductR, well, maybe for the more technical people, ConductR is itself an Akka cluster application. So on each node that makes up your cluster, you're going to have a little agent running, one ConductR node. And you can remote control this. So there's a JSON REST protocol, and you can use this to remote control ConductR and to upload bundles into your cluster, to start them, to scale them up or down. So it really fills a gap there between the infrastructure management tools and your actual application, where your infrastructure management tools like Puppet or Chef or Ansible or what have you, or could even be maybe you're using a cluster manager like Mesos. These will manage your infrastructure, and they will provide help for the initial provisioning. They will help you to get your application to the appropriate nodes. But then you have to manage. You still have to manage the lifetime of your application. You want to, as I said, you want to scale your services up and down independently. You might want to have an update of a single service, and you have to manage that. And all these things, this can be done with ConductR on top of these infrastructure management tools. So ConductR will really take care of where to deploy your bundles, and you don't have to worry about which node is going to run on exactly ConductR. You just upload your application to ConductR, and we'll put it on the appropriate nodes, and with other commands using the remote protocol, you can start it and provide the number of instances you want to run. As I said, it introduces its own, or it has a concept of a bundle, right? The unit of deployment. So these bundles combine the application and the configuration. Interestingly, or maybe interestingly, if you use Docker, you can use Docker images as the bundle format. So right now, with ConductR 1.0, we support 2 different bundle formats, one being Docker, the other one being a custom format we built for ConductR, which is a zip file that is hashed and signed, if you will. So you take the binary, the configuration, it's zipped, then we hash the contents and add this hash for consistency checks and for unique identification to the file name of the zip. As I said, you don't have to worry about the distribution of these bundles. ConductR will take care of that. And the way it does it it's quite sensitive about sort of being available all the time. So even if you have a big application that's going to be deployed and distributed within your cluster, this will not slow down the operation of the rest of your already deployed services, because it's back pressure aware and will not put too much load on your cluster. It will be sensitive there. We build up on some proven technologies. As I said, Akka cluster is one of them, and another one is HA proxy that we use for load balancing and for redirecting requests. So for each conductor node, you also get an instance of HA proxy, and this will take care of the load balancing between the nodes. And maybe even more importantly, you don't have to keep track of where your service is running, because HA proxy will know. HA proxy will be configured automatically by ConductR. So if you have 3 nodes, A, B, C, and a service is running only on node C, then all the other nodes are going to know about that too. And the HA proxies on these nodes will redirect requests to node C. So you can still access the service on node A or on node B. HA proxy will redirect your request to the service on node C. And of course, you can access this on node C as well directly. Location transparency, of course, is that. ConductR will take over the responsibility for the number of instances that your application is running with. Of course, you have to define that. You say, I want to run 5 instances of this service, or 3 or 6, and you can change that at one time. You can scale them up or down, and then ConductR will start these services on the appropriate nodes. It will also keep redundant copies, non-running copies of the application. So in the worst case that a part does fail, that the node in your cluster goes down completely, then it will already be available on some other node. So it can be fired up instantaneously. It doesn't have to be redeployed or downloaded from some repository. We will always keep a couple of unused copies of your bundles on other nodes. And lastly, it provides a little API for service discovery, because given the automatism that the ConductR will make sure, ConductR will distribute your application across the nodes. Of course, you cannot hard code the server names or the IP addresses. So you can use ConductR to find the services you want to use by name. Service lookup. So again, it's the purpose of ConductR is to fill the gap between the infrastructure management and your application. And this infrastructure management, ConductR is pretty agnostic there. It can run on hardware, on Linux. It can run on Amazon EC2s, of course, also Linux. But with the next version, 1.1, you'll also be able to run it on the Mesos cluster. Apache Mesos is a cluster manager that is already quite popular, I think, in the big data world. And that that abstracts from your actual cluster and gives you a resource negotiation API. You can add nodes and remove nodes from the cluster with Mesos, and it will make these resources available to the so-called frameworks. Any application running on Mesos is called a framework. So ConductR will be able to run as one framework on top of Mesos, and this is actually a very powerful combination where you can get very good hardware utilization, because you can combine, for example, if you run big data applications, you could combine Spark running as a Mesos framework with ConductR running as a Mesos framework, and they could share the same hardware with other frameworks as well, of course. And then on top, you get the applications you actually want to run, hopefully built with Akka and Play and Scala or Java. 2 more things. It's not to be mistaken for an application server. As we said earlier, isolation is a very important criterion for reactive applications. So each of the bundles you deploy will run in their own JVM. ConductR will manage that and can start and stop them. But if an application goes down, if it crashes completely, including the JVM, it will not take down any other. And ConductR is optimized for Typesafe Reactive Platform applications and will actually give you some niceties in combination with Akka cluster applications. It will take care of seed node configuration and things like that. But it's not restricted to that. We run ConductR internally, and we run other applications with that as well. One example I can think of is ActiveMQ. So you can basically run anything with ConductR. Okay, so if you've become curious and you want to try out things, you want to play around with Akka, I recommend you go to typesafe.com and download Typesafe Activator. That's a technology discovery tool, as well as also the build tool for play, actually. But in addition to that, it has a nice web UI, and you can use this to discover templates and examples of our technologies. And you'll find a lot of examples for both Akka Play and also for Play and Akka in combination, both with Scala and with Java. And it's a really good tool to discover things, and you get the source code and some tutorial with it where the author will explain the interesting parts of the example. And lastly, I just want to point out that this is not all just theory, or this is not about our idea, what we think should work or could work. This has really been adopted across the industry with huge success. And this is just a small snapshot with a couple of our customers that have used our technology to build reactive systems and have been successful with it. So if you want to know more, well, I'm going to be around for another 15 minutes or so feel free to ask any questions here in the webinar. And of course, later on, if you want to get more information, you can always go to typesafe.com. You'll see here a Getting Started section where you can download Activator. You'll find all sorts of information about ConductR, and of course also about Scala, Play, and Akka. And we also, well, if you'd like to meet somebody from Typesafe in person, or maybe have a presentation or some demo at your company, please do get in touch. We also have an office here in the UK, in London, in fact, so that could also be arranged. And that's all for me. And I'm going to check what kind of questions we have, if I can find my control center, that is. And I can't. Yeah. Okay, so we have one question about where to keep state. So in functional programming, you want to be immutable, and I said with play applications, you want to be stateless. So of course, the question remains, where do you keep your application state, though? So one possibility is indeed Akka. Actors are a great way to encapsulate state in an application and to work with that in a lock-free and asynchronous manner. So you could use Akka to manage your application state, and if you want to persist your application state, that's of course also possible. That's possible with Akka. There's Akka persistence, but the way you persist your state in application really depends on your overall architecture. If you have a more CRUD-based application, create, read, update, delete with a database, then you might go for a more traditional approach, which of course you can combine. You can combine, well, we, as Typesafe, for example, we provide Slick, an asynchronous interface on top of JDBC for SQL databases. So you can use that. You can just use relational databases to store application state. But you can, of course, also use approaches that have become popular in the last couple of years, such as event sourcing, and which is very well supported by Akka persistence. So you could use event sourcing. That means basically that you change the state of an actor, and you will not store the actual state, but you will store the event that led to the state change. So to reconstruct the state, you just replay the events. And usually you don't use a relational database to store the events, but something like Cassandra or another distributed data store that allows very fast writes and scales very well for more semi-structured data. I hope the question has been answered by this, otherwise just ask again. How does the reactive programming play with microservices? Picoservices, nanoservices, yeah, well, let's say small services. That plays very well. Actually, I mentioned Activator. So there's a very nice Activator template called Microservices with Akka. And we have I've only mentioned the Play framework, but if it's really about microservices and building RESTful services, there's also Akka HTTP, which is brand new, which is a successor to Spray that some people might maybe have heard of. So you can build very performant, very lightweight microservices with this stack. And you can actually scale them very nicely if you use Akka cluster with them. So I think it's a great fit for microservices. And if you watch the community section of the Typesafe website, I think in a couple of weeks, our chief architect and deputy CTO Victor Klang, one of the very first Akka contributors, is going to hold a webinar about microservices with the Typesafe Reactive Platform. So about ConductR, the question is, you've integrated ConductR into your development workflow. What's the minimal time to have it on production? So if the minimal time, so you're going to run some tests and stuff like that, but on ConductR it's really a REST call, and you push up so you upload your bundle into ConductR, and then you say ConductR start. So the minimal time, if your network is fast enough and your bundle is really small, is really seconds. Could be, I think in theory, yeah, you could sort of deploy and start a bundle in less than a minute. I haven't measured this myself, but there's really no reason why it should be. There's nothing holding it back. It's yeah. Right. So it seems there are not that many more questions. If anybody has one, so you could still enter it. All right then. So of course you can also always contact, or maybe one thing I should mention, if you're looking for developers, you can of course always come to eSynergy, and they will help you with that. If you have any questions regarding Typesafe services, of course we provide support for all of this. And yeah, please go to the Typesafe website, please get in touch, and we'll be happy to help.